Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there.
Hello, everybody. Welcome back to another episode of the A-Level Cookbook. Today, we're going to be doing the AQA A-Level Chemistry, Paper 1 from 2023. So this question's about complexes of the transition metal chromium. State the meaning of the term transition metal complex. So all they are is you've got a central metal ion surrounded by coordinately bonded ligands. That's what I would personally say. There you go. Okay, so CrPF3 is a complex of chromium that contains molecules of PF3. The electron pair repulsion theory can be used to predict the shape of a PF3 molecule, draw the shape of a PF3 molecule, include any lone pairs of electrons that may influence this shape, and then name this shape. So as always, with all of these styles of questions, you need to work out how many bonding pairs there are and how many lone pairs there are. So if we look at P, or phosphorus, it's in group 5. So 1, 2, 3, 4, 5, right? Now, it's bonded to 3 fluorines, fluorines are group 7. 1 electron is contributed to all of those. So 1, 2, 3. So you can see that there are 1, 2, 3 bonding pairs and 1 lone pair. So if I draw it like all exam friendly and stuff now, it would just be an electron cloud there, an F, an F, and an F. Now the shape here, whenever you're doing shapes, it should always be based on the number of bonding and the number of lone. So we have 3 bonding pairs and then 1 lone pair. That shape is pyramidal, or trigonal pyramidal. So just by the oxidation state of chromium is 0 in CrPF3. So a lot of people talked about the whole thing. A lot of people talked about the PF3. A lot of people talked about every element other than chromium for some reason. It says in the question, suggest why the oxidation state of this is 0. So the overall charge of this molecule is 0. So it must, and also from the bits above, PF3 has also got no charge. So if PF3 has no charge, then, chromium's going to have an oxidation state of 0 because, the whole complex, the whole thing is neutral. So you would say that PF3, is neutral and the whole complex ion is neutral. So there isn't really a need for a charge, if you will. The compound CrNH3 4Cl2Cl contains ammoniac molecules. But a lot of people struggle with these kinds of things because of how many letters and bits and bobs are going on here. This whole thing is a complex ion, and that's a Cl attached to it. That should ring to you that this is probably an ionic compound, as in this whole complex has a charge of +1, right? And that's going to have a charge of -1. It's the 2 ions together. Now it says, deduce the oxidation state of chromium in this whole thing, Cl. Now there's a reason why I just told you that, because this whole complex ion must, the whole thing must have an entire charge of +1 overall, and that is just going to be -1. So I don't even have to worry about that. I can just look at this. Now, another shortcut is that you don't have to look at absolutely every single thing in here and every single atom to work out the oxidation state of chromium, because you've got a Cr with 4 NH3s around it and 2 Cl2s. These NH3s are all not charged. So really, you're only looking at these Cl2s, which are both -1s. You've got 2 lots of -1, remember? And this whole thing, there's a charge of X on this Cr. So these two must give you a grand total of +1. So that, on that basis, the charge has to be, that's going to be X minus 2 equals 1. So X equals 3. There you go. So the charge of that is +3, then the oxidation state is +3. It says, name the type of bond between N and H in ammonia. In ammonia. So you have NH3 within it. So if it's N, H, H, and H, those are bonds between the N and the H, not intermolecular forces, not hydrogen bonds, not daisy covalent bonds. They're just simple standard covalent bonds. Covalent bonds. There you go. So now the compound Cr, this blah, 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 has a complex ion that shows isomerism. Draw the 2 isomers of this complex ion. So you've got Cr with 4 NH3s on it and 2 Cl2s. Remember, that's irrelevant. That's just like another part of the other ion. That's the other ion for this. You've got 6 ligands. You haven't got any bidentate ligands. They're all monodentate. So in that case, you're going to have cis-trans isomerism. So all you do is you just start with your central metal ion. You draw out the bonds and stuff, and then you just add everything on. Whoops, that's a terrible wedge. So then we've got, I usually start by forcing myself to draw the the lone pairs, and then the rest can come on after. So like that. And the overall charge of that is a plus. So there's one of them. And then the other one is simply just, these Cls are together. Now we need to put them on opposite sides. So I just draw the same thing, Cr, and then I've just got the Cl here, a Cl there, and NH3 here, and NH3 there, and H3N here, and H3N there. And then I just put the brackets around that, boom. What type of isomerism is it? Well, it's cis-trans, boom. It says complete the equation to show the formation of one complex that contains chromium in its +3 oxidation state. A lot of the time people struggle with this because they're like, I don't know this equation, I've not memorized it. Like, don't do that. Use what the question's telling you. They've told you that you're going to react this and this. You have no other choice. You can't mess around with it. And they've told you that you're forming one complex that has chromium in the +3 oxidation state. So you're making this, whatever this thing is you're making, chromium has to be in its +3 state. So what you do is you just have a look at what complex ion you're probably going to make. So you've got CrCl3, we're adding 5 H2Os on. Well, metal, the complex ions is probably going to have the H2Os in it. That's the only way I can use up everything, if you will. So then it would be Cr, H2O5, but we like 6, don't we, right? So what are the options left? I've got 3 Cls that I can use up. So it's probably going to be a Cl there, right? So that's my complex ion with an overall charge of, well, it's just going to be +2 because that's +3 and there's -1 there, right? But I still have 2 Cls left. Well, those 2 Cls conveniently are both Cl minus, which means they can just actually form an ionic bond with this whole complex there. So this thing's overall charge is 2 plus, and then I've also got 2 Cl minuses to go with it. So then what you end up with is you've got this whole complex ion here, and then just Cl2. Boom, there you go. Use the question what it's telling you to do these kinds of questions. You'll find that you can actually derive the answer a lot of the time, and you should. Okay, so figure 1 shows a cell to measure the standard electrode potential for the half cell, and it's this half cell here. So we've got magnesium being reduced into, Mg2 plus being reduced into that. Great. So here we've got our nice hydrogen here, we've got platinum, and we've got all of this stuff going on here. Now, just as a side note, you might be wondering why we use platinum. For example, if I'm doing a half cell and it's got Fe2 plus and Fe3 plus, generally speaking, if it's charged, it's going to be like aqueous in this topic, right? If they're both aqueous, what are you going to make an electrode out of? You can't have an electrode made of an aqueous thing. So that's when you use platinum, because the platinum is an exchange surface for these. So you could swap from Fe2 plus to 3 plus. Whereas, for example, magnesium, in the magnesium one, they've got Mg solid, and then they've got Mg2 plus. So you can just use that as the electrode. You don't need platinum because there's something solid there for you to use. So that's just important to note, is that's why you've got this platinum electrode here, because you're switching between H2 and H+. It says, state the purpose of the salt bridge and identify an ionic compound that can be used for this. There's a big misconception here where people say that it allows the transfer of ions from here to here. We don't want that. That's going to mess up the whole thing and stop it from working. So for this salt bridge, we tend to use KNO3 because it's soluble. We need it to be able to move, and it also doesn't really react with either of these. And what happens with the KNO3 is it allows these ions to move between each side, towards one side or to the other, not like mixing in and, disappearing through this, just moving side to side, because it allows the NO3 minus to move towards the side where it's more positive, for example, and then the K plus to move to the side which is more negative, and that balances out the charges on either side. So as, electrons move this way, these will move that on that side, whichever way it may be. That's what the whole purpose of it is. So the reason we do it is to complete the circuit, or you can say to allow electrical neutrality as well. So complete the circuit. And what we tend to use is so the identity is, so a lot of people have said that electrons move through the salt bridge. Incorrect. That's not what happens. And a lot of people chose random things that would react with these two. Like this is soluble, so it can move, and it doesn't react with what's in there. Okay, so state how, if at all, the EMF of this cell will change if the surface area of the platinum electrode is increased. Now, in order to run a standard hydrogen electrode, there's a couple of rules they've got to follow, is that every single solution has to have a concentration of 1 mole per decimeter cubed. You've got to have a temperature of 298 Kelvin, and the pressure must be 100 kilopascals. Any one of these getting screwed up will change the EMF of the cell, right? That's how it works. So as long as these are maintained, it doesn't matter what you do with that platinum electrode, it will always stay the same. So as in, there is no change because none of those are getting screwed up. That's why we run it in standard conditions. The reason for this is because the EMF is determined by the half cell potentials. So E right-hand side minus left, obviously that's just 0. But the overall EMF depends on the difference between these two. If the rate of this going up or down is also going to influence the rate of that going up and down. They'll change proportionally. And, all it really does is change the speed of stuff. It doesn't really mess around with how much of each E cell you're having. The only thing that screws up those E cells is these 3 things. That's what you should know and remember. So now it says the standard electrode potential of this half cell is shown. Water is added to the beaker containing the magnesium chloride solution. What's the effect of the magnitude of the EMF of the cell? So if we have a look at what's going on here, so remember that the E whatever in this situation is going to be, when we always consider, this to be 0 and then that to be whatever. And we always put the standard hydrogen one on the left. So that means that the the E cell, is going to equal E right-hand side minus E left-hand side. Now, obviously, the left-hand side is just 0, so it's going to be E cell equals E right-hand side. Now, they've told us here that this is the standard electrode potential, and they've told us that it's negative, which means that this one's going to be undergoing oxidation compared to the other one, which is just 0, because the standard hydrogen one is 0. So if that's undergoing oxidation, that means that you as you'd expect, that's going to be negative, right? However, the standard hydrogen electrode stuff only works as long as you keep the concentrations at 1 mole per decimeter cubed. So if I add water to this beaker, I am diluting it. If I'm diluting it, I'm actually decreasing that concentration. If I'm decreasing that concentration, then you're going to have less of this oxidation happening. If you have less of this oxidation happening, this is becoming less negative. If that's becoming less negative, the EMF value goes up. It becomes more positive, hence the EMF increases. And that's how you do that. The voltmeter V in figure 1 is replaced by a bulb. Give an equation for the overall reaction that happens when this cell is operating. So when you have a voltmeter, you have like pretty much infinite resistance amongst these. The reason being is because it's measuring the potential difference, and that's the amount of basically the difference in charge. So if one side's way more positive than the other, it will have a massive potential difference because it's the potential for the electrons and stuff to move. Very simplified, but like to get the point across. Now, if I put a bulb here, it doesn't have that massive resistance, so things can start flowing whichever way they may be. Now, you've got to use the cues in the question. Remember that standard hydrogen electrode potentials are always 0. Here, they have told you that this is minus 2.38, which is more negative compared to 0, meaning it is being oxidized. If you put a bulb there, then it's just going to do its thing until it finishes. So on that basis, we know that if we let it do its thing, this is going to oxidize and the one's going to reduce. So what I mean by that is we'll have the Mg solid, because I know that's definitely oxidizing, becoming Mg2 plus, aqueous, right? Now, the other thing in this, which is our hydrogens, is going to be reduced. So that means we're going to go from H plus to whatever that makes when it's reduced, which is plus 1 to 0, so it's going to be H2. So in order to balance this, I can add a 2 there, and then that, and then I get this, and then I get that. And then if I add my state symbols, and then that. The Mg plus 2H plus gives you this. Alternatively, you can just use the simple stuff as well. So like as in the Mg solid, and the other one is this H plus all comes from the acid, right? And that's where the H pluses are from. So it's going to be HCl aqueous and then Mg2 plus aqueous, and the Cl stays the same. It's not involved in this, MgCl2 aqueous. And then you just got whatever's left behind, which is just this gets reduced. So it's going to be H2 gas. Whoops, and that's a gas there, like that, and then you balance it like that. So either one is fine, but you have to appreciate that this Cl stays as -1. It's not being involved. There's no Cl business happening here. Nothing of the Cl's getting oxidized or reduced. It's the H plus and the Mg2 plus. So you've got to use the cues in the question like that. This question's about period 3 elements and their oxides. Give an equation for the reaction between a phosphorus and an excess of oxygen. So it's not the P2O5 business. It's always P4O10. That's just one you've got to learn. Unfortunately, P4O10, you're going to make. Now, phosphorus exists as P4. So in order to make this, you just add 5 O2s. Unfortunately, there's no other hacks to that. That's just how it is. Now it says, give a equation for the reaction between sulfur dioxide and water. So if you're ever stuck, just look at the question, what it's told you. So you know for a fact, no matter what, you can react. You're reacting, SO2 and H2O. But there's no debate about that. That's what it's showing you. Okay? Now, unfortunately, yeah, this is another one you've got to know, but you can kind of infer here that you're just adding SO2 and H2O. What could you probably make? H2SO3. There you go. It says don't accept H2SO4 because where are you going to get that 4 from? So that's what it is. And also, this is what the reaction is. But like, whenever it says give an equation, like put what's already there first, and then you could probably work out the other parts. Now it says give the display formula for the anion formed. So anion is the negative one formed when sulfur trioxide, which has the formula SO3, reacts with water. So if I'm adding SO3 to H2O, I'm going to be making H2SO4, which makes H pluses as its cation, and then SO4 minus as its anion. So sulfur is in group 6, 1, 2, 3, 4, 5, 6. It's got 4 oxygens chilling around it. So you've got this, and it's also got 2 minus charge. Those 2 minuses are on the oxygen part of it because we lost those H's. So you're going to have OHs originally. So the H2SO4 originally would have had an OH. Now it's just an O minus, right? And that's going to form just a single covalent bond with this like that, okay? So a single covalent bond there. And then the same for the other O minus that we've now got. Right, we have 2 O's left and we need to fill out these. It's actually double bonds there, like this. So in summary, what it looks like is H2SO4 is just an S in the middle, a double bond there, because remember, each one of these is a covalent bond, a double bond here, or wherever you want to put it, an O minus there, an O minus there. There you go. Because these were originally OHs, but then obviously we lost them to make the anion. So it says, give an equation for the reaction of magnesium with steam and explain one of the observations made. So again, start with what the question's telling you. It says magnesium, which we're reacting with steam. So you're going to be reacting it with H2O. Right? Now, this is, again, a specific example you need to know. what it makes is it makes magnesium oxide and then whatever's left over. So we've used up our O and we've got H2 left, so it's probably going to be H2. So then what's the observation you're going to make? It can't be effervescence because you're reacting a solid with a gas. Where are you going to see the bubbling? Like, you're not going to see bubbles because there's no liquid happening here. You need to also know that that's a solid as well. Yes, that's a gas, but like, it don't work. So what you end up seeing is you form a white powder, because that's what MgO looks like. Next, give an equation to show how an excess of magnesium oxide reacts with phosphoric acid. Again, start with what the question has told you. So we know that we're reacting magnesium oxide with phosphoric acid, H3PO4. Now what you do is you look at them and think, what's going to do what? So this is Mg2 plus, that's PO4 3 minus. In order to get those to sit nicely with each other, so, PO4 minus 3, and then there's a plus 2, 6 is the common number to these, right? So it means I'm going to need 3 of them, Mg3, and then 2 of those. So Mg3, PO4, 2, right? Because you're adding an acid to a metal oxide. Whenever you add an acid to a metal oxide, you make a salt and water, and then you just balance the rest out. So we need at least 3 magnesium oxides there, and then PO4 2, we need at least 2 H3PO4s, right? The PO4s are happy. We've got 2 of them, 2 of them. The Mgs are happy. We've got 2 of them, 2 of them. We're left with 6 waters and 3 oxygens, which actually conveniently gives you that. Done. So now it says nitrogen dioxide decomposes at high temperature, and here's this equation. At 0.317 mole sample, a nitrogen dioxide is placed in a sealed flask and heated at constant temperature until you hit equilibrium. At equilibrium, there's this much of oxygen. Calculate the mole fraction of each substance. It's really disappointing that people just dive in and just work out random numbers using this and this. That's not how it works, right? You've got to read the question carefully. So whenever you're doing an equilibrium, you're always going to have, you don't just magically hit equilibrium. You've got to let it build up. So for example, here, if I put this in a whatever container, it's going to go this way a little bit and then that way a little bit and this and that and then blah, 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 until they equal each other. So at the very, very, very start, there's none of this because I didn't put any in there. That's why you do the whole start, change, end business. So here, the question's told you that that's 2, not 3. A 0.37 mole sample is placed in a sealed flask, right? So 0.317 moles, right? When you're doing this, force yourself to go through every single step. Don't just leave things blank, as in one by one. So we have this much of that. Do we have any of this at the start? Well, no, because the question hasn't told you they've added any. So 0 and 0. Then it says, at equilibrium, the flask contains this much of oxygen. So go through and add that detail in. So at the end, at the equilibrium, you're going to have 0.120. So what was the change from there to there? Plus 0.120. Okay, so if that went up by 0.120, every one of these will also have 2 of those made. So this will go up by plus 0.240. Okay, so that means plus 0.240. Now, it takes 2 of these to make 1 of those. All right, so if this went up by 0.120, it took 2 of them to make that, as in this would have gone down by 2 times that. So this would have gone down by minus 0.240. So at the end, the moles of everything is going to be 0.077. So then the mole fraction of something is just the mole of whichever substance it is over our total moles. So our total moles is going to be 0.437. So now the mole fraction of everything is going to be, well, for the we've got NO2, we've got NO, and we've got O2. So for NO2, it's going to be 0.077 divided by 0.437, which is 0.176. And then you just repeat the others. So for the NO, you just do this divided by that, and then this divided by that, and you end up with all of them. So that's going to be 0.176, that's going to be 0.549, and that's going to be 0.275. There you go. So the total pressure in the flask in question for part 1 is 120 kilopascals at equilibrium. Calculate the partial pressure of NO2. So they've told you that the total pressure is going to be 120 kilopascals. To work out the partial pressure of something, it's just its mole fraction times the total pressure. Our mole fraction of the NO2 is 0.176. So you would just do this 0.176 times 120, which gives us 21.1 kilopascals. Boom. The table 1 shows the mole fractions of 3 gases in a different equilibrium mixture, not the same one. It says for this equilibrium mixture, Kp is that, give an expression for Kp, and then use this to calculate the total pressure in this flask. So let's have a quick look at what the business we got going on here. It's going to be the partial pressure, not the concentration, because we're dealing with P and its gases, of NO squared, because there's 2 of them, times the partial pressure of O2, all divided by the partial pressure of NO2, this thing, squared. That's how you do it. Now here so we've got that first bit done. Now it's saying use your expression and this data to work out the total pressure of the total pressure, right? So we're kind of stuck because you're like, dang, I don't know how to do this, right? Well, let's just have a quick gander at what we've got. We've got Kp and we've got all of this business here. If we have a look at what's in the table, they've given us mole fractions. So remember that a partial pressure of something is going to equal its mole fraction times the total pressure, isn't it? So here, the Kp, which they've told us is 59.7, 59.7 is going to equal the partial pressure of this NO, right, which is this, which remember is going to be mole fraction times total pressure, which I've called X. So it's going to be 0.460 times X, the total pressure, all squared, times the O2, which is 0.230 X, all divided by this NO2 here, which is going to be 0.310 X, all squared, right? Cool. Now, I can tidy this up a little bit by, well, let me think, what's a nice way of doing this? I could do this side times that side. So if I do if I times both sides by, times both sides by 0.310x all squared. So if I do that, I get 59.7, 0.310x squared equals 0.460x all squared, and then 0.230x. Now, if I just tidy these up, as in I square this and then I multiply those together, I get 5.737 x squared equals 0.04867 x cubed, as in I've squared that this whole thing and then times it together and tidy it up like that. If I now divide both sides by x squared, I get 5.737 equals 0.04867 x. And then I just divide both sides by that. So then x will equal 5.737 divided by 0.04867, which is roughly 117.8 something, which is roughly 118 kilopascals. Boom. So now it says the equilibrium mixture in this part is compressed into a smaller volume. Deduce the effect, if any, of the change of equilibrium yield of oxygen and the value of Kp. So whenever you're doing your equilibrium questions, a lot of people love to just jump straight to saying, oh, shift left and right. Like, don't do that. Look at what it's asking you. It's saying how much does the oxygen change, but also you should think in this way instead. Anything you do to an equilibrium, it will move to counteract the change. As a side note, if you say counteract a change in an exam and you don't say what the change is, 0 marks, easy speed run, right? So here, the question is saying here that we've made into a smaller volume. So we have increased the pressure. If I increase the pressure, the equilibrium will try to shift in whichever way it can to decrease it. Okay? So if I want to decrease the pressure, I need to look at this and think, how do I decrease the pressure? Well, there's fewer sides on this mole, and there's on the other side, fewer moles on this side, and then there is more on that. So in order to decrease the pressure, we'll move towards the side with fewer, as in that way. So then the yield of the O2 will fall. So that decreases. Obviously, you write the whole thing. I'm just lazy. Now, what is it? What's the effect on Kp? There is absolutely no change because Kc, Kp, Ka, Kw, K, whatever is only affected by temperature. Absolutely nothing else. Everything, the way I like to think of it, so super simplified, is that yes, everything goes up and down, but it all balances out to give you the same Kp value again. Like as this goes up, those will go down and so forth. Whereas the only changing temperature doesn't balance it out nicely because you can see that's endothermic. So if I increase the temperature, for example, you'll shift this equilibrium to the right? Because it's going to use up that extra heat to try and balance the equation, to counteract that change, right? Because it's endothermic. That doesn't mean it's also going to start moving backwards because that would be the other way, as in you're decreasing the temperature. So that's one way of, if that makes sense, of thinking about it. Like you can't really, like with all the other ones, you can move forward and backwards and balance them out. But with then, the temperature stuff, you're forcing it in that way and only really. That's how I think of it. So the only thing that affects it is temperature. Whether you use pressure, catalyst, concentrations, whatever for Kc, Kp, Ka, Kw, nothing affects it except temperature. Which is why you'll find nearly every question on it will say, at this temperature, Kp, Ka, Kc, Kw is that. Because then students can't argue and say, oh, but what about the temperature's changed? Or something like that. So the equilibrium mixture is allowed to reach equilibrium at a lower temperature. Explain why this yield decreases. So whenever you answer an equilibrium question, say what's happening. So first of all, you've decreased the temperature. That's your change. So the equilibrium will shift, not to left and right, please, will shift to try and increase the temperature. Before you even look at the equilibrium, you should say this to force yourself to know what, to know what you're looking for as well. So now I want to move this equilibrium to make the temperature go up. Now, this reaction is endothermic. It absorbs heat energy moving forward. So backwards is exothermic. It's going to release it. So that means that what's going to happen chemically is that these two are going to react to make more of that, as in it's going to move in the opposite direction, right? In the endothermic direction. So it's going to move in the opposite direction. And then to be safe, really say what's happening reaction-wise as well. So as in the 2NO and O2 react to form 2NO2 as this is exothermic and releases heat. That way you kind of cover all ground for heat energy. And then you can't really miss stuff. This question's about metal chlorides. Here's some enthalpy change data. Now, if you guys know me personally, I've seen any of my other videos, I always hate on how people do this. I think it's a load of crap the way people do these with memorizing every single possible cycle in the universe. I think that's a terrible way of doing it. All you do is you look at the overall equation that you want and make sure everything is in it, first of all. So number one, they're saying find the molar enthalpy change when calcium chloride dissolves in water. So you should think, that's the enthalpy change I want to find. What's the equation of that? It's the enthalpy change when 1 mole of calcium chloride, solid ionic lattice, dissolves completely in a solution, blah, blah, infinitely dissolution, yada, 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 to make aqueous ions, like that, right? That's that first step, as identify what you're actually looking for. So that's the enthalpy of solution. Now, the next thing you do is you look at the enthalpy changes they've given you in the table. Are they any like of these parts, if you will? So here, we're going from gaseous ions to aqueous ions. That's the enthalpy of hydration, which means it's when 1 mole of gaseous ions is converted to aqueous ions under standard conditions, yada, yada, yada. So you're going from gaseous ions to aqueous ions. Here, gaseous to aqueous, it's the same one. So gaseous ions to aqueous ions. And then from here, it's gaseous ions, solid ionic lattice. That's the lattice enthalpy of formation when 1 mole of a solid ionic lattice is formed from its gaseous ions. So that means you're going from gaseous ions to solid ionic lattice. Then what you do is you remember that these enthalpy changes tell you how much it takes to go from gaseous ions to aqueous ions here. So you look at this and you say, which one of these do I already have? One by one. So here, that's solid ionic lattice. I already have you, right? Here, that's aqueous ions. I already have you. That's aqueous ions. I already have you. Can you notice how this gaseous ions aren't here, yet all of these equations have gaseous ions in it? That's probably what's going to go at the bottom of your cycle. So you should never really design a cycle without doing that. If you go into a question and you can figure out how to do the enthalpy cycle based on that text alone, you're doing it wrong objectively. I'm sorry to say it to you. I'm sorry to break it to you, but you're doing it so unbelievably wrong. It should be 3 marks because you just got to do it like this. Then what you do, now I know gaseous ions, how to decide which way the arrows go, look them one by one and each at a time, right? So what I mean by that is every single arrow is an enthalpy change, it's a number. So I'm obviously going to put the number that links with this, right? This one. But you can't just draw the arrows going up or whatever. You need to look at, or down or whatever. You need to look at what the question's telling you. It's saying in order to go from gaseous ions to solid ionic lattice, you need this much, that enthalpy change is that. So gaseous ions, solid ionic lattice, I'm going to be going upwards here, minus 2, 2, 3, 7, right? Now let's look at this. So here and here, how do they link? Well, I can see that they've given me gaseous ions to aqueous ions here for this, right? The enthalpy of hydration. So it's not going to be down, it's going to be up because this number is from here to here. So minus 1650. And then the same for this. However, the enthalpy change says when it's 1 mole of gaseous ions are converted into aqueous ions. So if we've got a 2 here, it actually means we've got 2 times that because we're doing 2 moles of it instead. So that's why your definitions matter. If you complain being like, oh, I hate learning the definitions, you're doing it wrong, mate. Doing it so wrong. Hess's law says that as long as you start with and finish with the same thing, the enthalpy change will be the same no matter how you get there. All right. So the enthalpy change of a given reaction is independent of the route taken. All it means is same reactant, same products, don't care, same enthalpy change. So the route we can go is from here to here to here, and that will equal whatever this all equals will equal that. Because that's the same, isn't it? You're going from there to there eventually. So the enthalpy of solution is simply just the same as going here, here, and here. So we're going from here to here. Well, we're going against this arrow now. So it's going to be 2, 2, 3, 7, right? And now we're following this one back up, minus 1650, and then plus 2 lots of minus 364. I like to bracket off the minuses and just do it like that. It just makes life easier with the plussing and the minusing. If you do that, you should just end up getting a solid minus 141 kilojoules per mole. Boom. That's how you do every single one of these. If you do it this way, you'll first of all have to learn the definitions and you'll memorize them that way. And also 2, it means you actually know why you're learning them. And 3, it's like the best way ever and everything else is a load of rubbish in my opinion. And 4, you can't screw this up unless you write the numbers in wrong or like accidentally follow an arrow the wrong way around. Like this forces you to actually use your logic here. It says, use your answer to this question to deduce how the temperature changes when calcium chloride dissolves in water. You're dissolving this in water, which is this enthalpy change of solution, which is this here, and it's negative, it's exothermic, so the temperature increases because it's releasing water into the surroundings, of which is the water. So explain why the enthalpy of hydration of fluoride ions is more negative than the enthalpy of hydration of fluoride ions. I see this a lot as well, and it actually does my head in. Smaller atomic radius? Atomic radius? The question says ions, bro. What are you doing? So stop using memorized answers. It just don't work. You just can't look at it and be like, yeah, I know this because I'm a genius. I memorized it in my Quizlet flashcards. Like, it don't work. Read the dang question. It says the enthalpy of hydration of fluoride ions. It's told you that this is more negative, right? So remember that negative, or exothermic, if you will, is bond making. Endo is bond breaking, sorry. So here, if this F minus enthalpy of hydration is more negative, then it means we're making more bonds, as in the bonds being made are stronger and releasing more energy, right? So F minus, the reason it forms those bonds is because you've got those delta positive H's on your H2Os, right? And they form those bonds like that, right? The attractions between those two. So what you have to explain is that for some bizarre reason, whatever it may be, this forms like, more stronger bonds, if you will, there's more attraction with the delta H, the delta positive H's in the water, right? So start with the obvious, which is that regardless of whether you're going to actually know why, if you say that, you still get at least a mark. So F minus has a stronger attraction to delta positive, you write the whole thing, I'm just being lazy here, H on H2O. And then we need to think why. So why is it that it's that? Smaller atomic radius is an easy way of saying I don't know what I'm doing and I'm just memorizing things and I think I'm the goat. No, it doesn't work. These are ions. So for some reason, this F minus is way better at attracting that. So compare the two. The only difference is that this is bigger, right? So if that's smaller, it means that it has a higher charge density because like you're packing, like imagine I've got a cube here and I've got this like density, this like packed in it. It's really dense. Whereas if I have this bigger cube here and I put that same thing in, it's not as dense, right? Imagine this is attracted to that black like scribble in there. And if I put them right next to each other, they're quite close. Whereas if I do that, not as close because there's all that space in between. It's literally like that. So F minus has a smaller size and therefore it has a higher charge density. That's it. Saying atomic radius, easy speed running of getting things wrong. And also talking about electronegativity and shielding, also an easy way to get things wrong because it's not losing or gaining electrons because it's already gained them because it's F minus. And also ionic bonds, there's no relevance of ionic bonds because you're not forming ionic bonds. It's just the attraction between these and these together. So there you go. So figure 2 shows an incomplete Born-Haber cycle for calcium chloride. Complete this by writing the formulas of the missing species on each of the 2 blank lines. So, okay, you have to know your definitions here. There's no way around this. And you have to put the state symbols. If you don't say the state symbols, you're literally just wasting your time because the definitions depend on those state symbols. Like, for example, the enthalpy of hydration is where you get 1 mole of gaseous ions forming aqueous ions. You can't know it's that from an equation if you don't put the state symbols in. So that's why they matter. So if we have a look, compare the lines is what I would say. So here we've got calcium in its standard state and Cl2, and then you're making calcium chloride solid. That's just your enthalpy of formation, right? But now if we have a look from here to here, what's different? Cl2 is still Cl2. For some reason, Ca solid is now gaseous and has put out an electron. Well, we can't do any ionization energies here because the first ionization energy is where you've got 1 mole of gaseous atoms becoming gaseous 1 plus ions. Whoops. So in order to do this ionization energy, it has to be gaseous to begin with, meaning we have calcium gas here plus a Cl2 gas. Boom. Now, if we look at our next blank line, so Ca2 plus gas was 2E minus, and then you've got Cl2, and then for some bizarre reason, it's now become no electrons there, and we've also got 2 Cl minuses here. This is a molecule, it's still its thing. We have to atomize it, because otherwise you can't do this, because the definition says it's when 1 mole of gaseous atoms, remember, for electron affinity, become gaseous 1 minus ions. So these aren't gaseous atoms, this is a molecule, Cl2, so we have to atomize it. So we've got Ca2 plus gas plus 2E minus, that stays the same, but now we have 2Cl gas. Otherwise, it doesn't work. So that's why the definitions matter and also the state symbols. So now it says use the data to find the second ionization energy of calcium. So here to here, see here and there, you can see we're making 1 mole of a compound from its elements in their standard state. So that's the enthalpy of formation. So that's going to be this minus 795 here, right? So minus 795. Cool. From here to here, what we're doing? Well, we're going from a solid to its gas. We're a standard state to gas. So we're going to be atomizing the calcium. So wherever that is, atomization of calcium. So plus 193. Next. What are we now doing? We're now going from gaseous atoms to gaseous 1 plus ions. That's the first ionization energy of calcium, which is this one here, 500, plus 500, sorry. Then what are we doing? From here to here, we're now doing the second ionization energy, which we don't know because that's what they're trying to ask us to find, so we're calling that X. What are we doing from here to here? We're atomizing that chlorine, so we're now going to do the 121. However, the definition says it's when 1 mole of gaseous atoms are formed from an element in the standard states, right? So it's actually going to be, because we're making 2 Cls here, we're actually going to have to double that. So the atomization is actually going to be 2 lots of 121 here instead, right? Then here, we've got the electron affinity, and that's when 1 mole of gaseous atoms become 1 minus ions, but we've got 2, haven't we? So you have to actually double that, so it's going to be wherever that is. Electron affinity is going to be minus 364 times 2. Sorry, whoops, and I've already done that. So minus 2 lots of minus 364. Again, I like to bracket them off like that, it just makes life easier. And last but not least, you've got a solid ionic lattice formed from its gaseous ions. That's the lattice enthalpy of formation, which is this last one here, minus 2237. So 2237. Born-Haber cycles are just Hess's law cycles on crack. That's all it is. It's like if you just gave them a bit of speed and said, all right, go to town, do what you want. If you start and finish at the same point, it doesn't matter how you get there, it will be the same. So a lot of people just say this equals like blah, blah, blah. That's fine. You can do that as well. It doesn't matter. If I start here and I finish there, for example, it doesn't matter if I go this way or if I go that way. If I start from like here to here, it doesn't matter if I go this way or if I go this way because its start and finish are the same. All right, so that's why that whole enthalpy change thing here works, because you start there and you finish here. So the way you can do it is obviously just go that way, or you can go all the way around the other way like that. Okay, so from here to here, it's got to equal all the rest. So it's going to be minus 795 is going to equal following the cycle the other way around. So, okay, whoops, I don't know why I said 500, it's 590. My bad. So it's actually going to be minus 795 equals, well, then it's going to be 193 plus 590 plus x plus 2 lots of 121, plus 2 lots of minus 364 minus 2237. If I tidy that up, I get minus 795 equals x minus 1940. So x is going to equal minus 795 plus 1940, which is plus 1145. I always put the pluses and the minuses, don't risk missing that. There we go. So explain why the second ionization energy of calcium is greater than the first of calcium. And here, people were trying to beat around the bush, being like, I'm going to be sneaky and I'm going to say absolutely nothing, right? Like, you can't just give vague answers. You got to use your brain here. If we're doing the first ionization energy, right, it's when you've got gaseous atoms becoming gaseous 1 plus ions. Right? And then the second is going to be gaseous atoms and then gaseous 2 plus ions. Now let's just have a think what we're actually doing in simple people words. You're literally just peeling off an electron. You're yanking one off, right? So in order to do that, you need to put energy in. Now here as well, wherever it's gone, the first ionization energy you can see is positive. It's endothermic, bond breaking. You've got to put energy in to overcome that attraction between the electron and the nucleus, right? And then the answer we just worked out as well is plus 1145. That's even bigger for the second one. So here, you've got to yank another electron off. Have a think about why for a sec. This is 2 plus versus 1 plus. There's going to be way more attraction for the electron. The electron's going to be, bloody like, no, I don't want to go. And you're yanking it off. You're pulling it away. So you got to put more work into it now to pull it off. You got to put more energy in. So that's it. So the electron is removed from a more positive ion, which needs more energy. That's it. People just beating around the bush saying like, like saying random stuff and then just being vague and getting no marks. I don't do that. You got to be direct, straight to the point. Bang. So table 4 shows lattice enthalpies based on a perfect ionic model and lattice enthalpies from Born-Haber cycles for these 3 methyl chlorides. Okay, so just as a quick recap, you can work out theoretical lattice enthalpies by doing calculations, assuming that you have a purely ionic model, which assumes that every single ion is a perfect sphere, okay? And it also assumes that their charges are nicely even distributed across them, like there's no hotspots, if you will, of positivity and negativity, right? However, when we do experiments and we do Born-Haber cycles, it doesn't actually match that well, right? The experiments don't actually fit perfectly and actually show that there's an element of covalent character, as in they're not exactly spherical. There's a little bit of like a bit of dragging like that almost, okay? So as a result of that, you get these sort of weird looking things here like that. So what it's trying to say is that it's showing evidence that there's actually a bit of covalent character to it, as in there's a little bit of covalentness, right? And how that works is because they're not exactly spherical, positive ions will polarize the nearby negative ones to differing amounts. If you have more polarization, you're going to have more covalent bonding here. So as in, for example, in this example here, they're perfectly spherical, nicely evenly distributed, whereas here, the electrons in this negative one are actually being pulled towards the positive one, rather than just objectively, no, you have this and you have this. Okay, so what all you've got to know is that in a perfectly ionic model, and then your Born-Haber cycle, there's a massive difference. Then it obviously implies that there's a large amount of covalent character, as in a lot of it's covalent. They're not actually all perfect spheres, because that wouldn't make sense, right? Okay. Whereas if there's a very little difference, then you're very close, as in these, there's very little covalent character, and they're all nicely like that. So here we've got to discuss the values in table 4. We need to compare the 3 values based on a perfect ionic model and then compare the values based on a perfect ionic model to the values from a Born-Haber cycle for each compound. Okay, so as in, let's compare them based on the perfect first, as in compare those, okay? And this is the lattice enthalpy of dissociation. So you need to make sense of what's going on here as well. Here, a lot of people just started yapping and then like kind of left it there and that was it. Because they're mistaking atoms and molecules and elements and stuff. Like, these are not molecules. They're ionic compounds, like 2 plus, 1 minus and stuff. So do it in steps. The first thing they're saying is compare these values based on that alone, and it's the lattice enthalpy of dissociation. So if we're dissociating, I need to put energy in, right? If you're going to put energy in, it's endothermic, and that makes sense because they're all positives. So here, let's start with the obvious. I'm going to write a 1 there, if you will, and then a 2 here. Okay, so for number 1, you can see that CaCl2 has the highest value, then it's AgCl, and then KCl, okay? Now we need to figure out why. Why is it that for CaCl2, you've got to put so much more energy in than the others. Well, if you have to put more energy in, say it. It requires more energy too. And then you're thinking, okay, well, I'm dissociating these and peeling them apart. What am I actually putting the energy in to do? What am I actually using it for? We're breaking bonds. Which bonds? Well, remember that the definition of this is when 1 mole of a solid ionic lattice becomes gaseous ions. It's gaseous ions, right? So this is going to be CaCl2 solid becoming Ca2 plus gas and 2Cl minus gas. So the bonds that you're overcoming in that must simply be the ones that are holding those ions together, the ionic bonds, right? So therefore, it requires more energy to break its ionic bonds than in AgCl and KCl. Even if you have absolutely no clue what you're saying, just by deriving it from the question and what you know, like the basics about, you can, figure it out like that. So you've now just said that, so therefore its ionic bonds are stronger. Right? We've explained the energy side of things. Now we need to think, okay, why is it that's the case, right? What you do is you compare them all. So this is Ca2 plus, that's K plus, and that's Ag plus. So already we can kind of figure out why they're all chlorides, so these are all irrelevant. The only thing that's changing between these is the Ca, K, and Ag. So compare them. This is 2 plus, these are both 1 pluses. The fact that that's 2 plus means it's surely going to attract this 1 minus way more strongly, isn't it? Okay, so that's it. So Ca2 plus has a larger charge than K plus and Ag plus, so therefore there's more attraction between it and Cl minus, not electrons, because we're not talking about electrons here, we're talking about Cl minus and stuff, okay? There you go, that's already explained every single other bit there, whereas the Ag plus and K plus are just, they're just one charge, they're just 1 plus, that's it. So that whole bit's done. Now it says compare the values on a perfect ionic model from the values to a Born-Haber cycle for each compound, as in 1 by 1. So for 2, let's do that. So if we look between here and here, the difference is 14, all right? And then for the next one, it's 11. And then for the last one, it's 135. So the differences between these. So on that basis, where you can see that these both have quite similar values, that's not huge, If you're looking at thousands, a difference of 14 is not massive, whereas that's pretty big. So then you would just point out the obvious, say what it is, right? That the CaCl2 and the, what was it again? Whoops, the KCl, there's, I'm just going to write perfect ionic model just to be lazy. Born-Haber cycle enthalpies, obviously you write the whole thing, are similar. So what does that mean? Is that there's very little covalent character, right? Whereas AgCl, the difference is larger, right? Which means it's got more covalent character. Now remember how I said that those positive ions are polarizing and it polarizes everything around? You would say that the Ag plus is more polarizing, I should say, and that's it. Boom. So a lot of these styles of questions just point out the fact first and then say its immediate relevance. So what I mean by that is that, for example, here, this lattice enthalpy of dissociation, this has the highest value. It's the highest lattice enthalpy of dissociation, which means you got to put more energy to separate it. And then it clicks in your head, you're oh yeah, it's because you're using that energy to break. And, the rest is there. There you go. Now, if you've seen my recent video, I'm going to be an absolute hater on how, we're going to do these titration questions that's coming up. The concentration of dilute hydrochloric acid can be found by using a titration of standard solution of barium hydroxide. Calculate the mass of solid barium hydroxide needed to prepare this solution of barium hydroxide solution. A lot of people forgot to convert volumes, bro. Come on, you all need to come on. So it says here, the mass of solid barium hydroxide. So we need how much of this stuff. So we've got this volume here, we've got that concentration. We need to work out the moles of it, right? So the moles is going to be 0.250, that over 1,000 times 0.1, okay? Which is going to be 0.025 moles. And it's asking you how much mass you need to get this many moles. Well, all you just do is mass equals moles times MR, which is going to be 0.025 times 171.3, which is 4.28 grams. Boom. The mass of barium hydroxide in this question is dissolved in a beaker that has 150 centimeters cubed of distilled water. Describe how this solution is used to make 250 centimeters cubed of that solution. So it's telling you that this barium hydroxide you've got, that 4.28 grams, they plunked it in 150 centimeters cubed in a beaker. Now it's saying, how do you get 250 from that? Because remember, that number we worked out is how much to get to that concentration. So what a lot of people unfortunately were doing were for some reason then just calculating and doing a lot of other random stuff. Use your brain. That mass, which I've just rubbed out conveniently, was to make that concentration. They've just told you that you've got 150 centimeters cubed. So you need to make it go up. So all you do is, first of all, it's in a beaker. So we need to put it in the big thing that we love using, a volumetric flask. So transfer the solution to a volumetric flask. But then we also don't want to lose anything. We want to make sure it's, the right amount. So you wash a beaker with distilled water and add the washings, because you want to put those in, and I write VF for short because I'm lazy, volumetric flask, you write the whole thing. And then what you do is you just make up to the 250 centimeter cube mark. And then what you do is at the end, that's not great. You don't want to just settle at the bottom. You want to invert it multiple times to mix. Because the idea is you've got this 250 centimeter cube sample at the end that you're going to take 25s out of, or 10s, or however many. You don't want it all to just settle at the bottom, because then if you take the top bit off, you've got nothing in it. So inverting it ensures that it's kind of evenly distributed. Otherwise, this whole experiment don't work. So then before the first titration, the 25 centimeter cube pipette is rinsed with a small volume of barium hydroxide, suggests why it's a good practice to rinse the pipette in this way. So before the first titration, this 25 centimeter cube pipette is rinsed with a small amount of barium hydroxide. So where are they using a pipette? Have they told us anything about a pipette? No, they have not. You need to decide who's in the pipette, right? If you don't know who's in the pipette, you can't really do this question. So you've got to look back at this whole question. What you put in the pipette is the thing you know the concentration of, right? So as in, let's see, the concentration of this could be a standard solution. So in this, you've got barium hydroxide inside the pipette. Now, for some reason, adding barium hydroxide to the pipette beforehand makes it a better thing. Well, it's just washing it out. Because if you wash it out with water, then you're going to dilute whatever you add in there, right? But if you just completely wash it through with this solution, then you're not going to dilute it. So it's so that water doesn't dilute the BaOH2. There you go. So then you can wash it safely, knowing that you're not going to dilute whatever you're doing. It says hydrochloric acid is added to burette using a funnel. Stay-wise good practice to remove the funnel from the beaker before the titration. So you've got this burette here, and you've got this funnel chilling, and they put hydrochloric acid in it. Why is it a good idea to take it out? Have a think. I mean, there's going to be bits of it just dropping in, isn't there? That's it. Drops of acid may fall into the burette. In a different experiment, this much barium hydroxide is used to make 250 centimeters cubed of this solution. 25 centimeters cubed of this reacts with exactly that much hydrochloric acid. Calculate the concentration of this hydrochloric acid. This should be 3 marks. The fact that 30% of people got all marks is just shocking. Like, what were y'all doing? If you do this style of question, you cannot, and I say cannot, work out moles until you figure out what the ratios are and who reacts with who. Full stop, okay? If you try going in being like, I'm going to work out moles and I'm going to do this and this, it's like, you're just going to, like, why? 30%, man. This should be 100%. Everyone should get this. What you do, and what I think to stop people making these mistakes, is to just make a little mental flow chart of what's happening, okay? So what I mean by that is look at every single thing's number and then force yourself to put something to it. So go read one by one, line by line. You can't jump back and forth, as in you have to go in order and pick the numbers out and say who they belong to. So what I mean by that is blah, 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 blah. Oh, I see a number here. Mass of 0.952 grams, right? Who does that belong to? Let's use our reading comprehension skills. It belongs to barium hydroxide, BaOH2, because it's this, right? Next, blah, 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 blah. It makes a volume of 250 centimeters cubed. Who's in that 250 centimeters cubed? This barium hydroxide, because it's a solution of this, and you can read. So 250 centimeters cubed, right? Then, and they're trying to help you because they know that people make this mistake and you still do the same rubbish. So blah, 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 blah. There's a volume here. I see a volume at 25 centimeters cubed. Who does this belong to? Read again. Blah, 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 blah. Of this barium hydroxide solution. So it's BaOH2. And it says it reacts with exactly, I see another volume. I know it says reacts with, so I know I'm going to add these together, or they're going to do stuff with each other. So V equals 24.5. Who does it belong to? Blah, 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 blah. Hydrochloric acid. If you do this, it means you can't fumble this possibly because you've just forced yourself to read the question. What I think people do is they try and do calculations. They'll blindly work out moles of something, right? And then they'll be like, okay, then I'm going to do this and this. And then they try and look back at the keywords in the question in the hopes they find the right thing. It's such a waste of time. And why are you doing that, right? So always do this bit first. And then number 2, the second bit, we're not done, is work out what the ratio of these two are reacting with each other. So this is Ba2 plus, and this is 2 OH minuses, and we've got an HCl there. So we're going to need 2 HCls for every one of them. So the reaction ratio is 1:2. Now the rest you can do, because we know that the moles of this is going to be it over its MR, right? So the moles of the moles of the BaOH2, but in which situation though, you have to also check. This is the moles of this, which was in here, wasn't it? In the 250, because I've got 2 BaOH2s. I need to be clear on who it is. This is the moles of the BaOH2 in 250 centimeters cubed, which is going to be 0.952 over its MR, which is 171.3. And if we do that, that gives you 5.56 times 10 to the minus 3 moles, right? However, that is not reacting with the HCl, according to the thing that I just made us write. This is. So what's different about this one versus this one? We have 10 times less. So you're going to forcibly say the moles of BaOH2, not just that, you have to say who it is, which one of them, in 25 centimeters cubed is going to be, well, now you know it's from 250 to 25, so it's going to be this answer here divided by whoops, its answer divided by 10. So it's going to be 5.56 times 10 to the minus 4 moles. So now you know the moles of this individual. You can now figure out the moles of this one because you know they're in a 1 to 2 ratio. So now you know that the moles of this HCl must equal 2 times this answer here, which is just going to give you 0.00111 moles. Now it's saying you want to find the concentration of it. C equals N over V. It's the concentration. So therefore, the concentration of the HCl is going to be its moles. It's the 0.01111 divided by its volume, which we've established here and written very nicely, 24.5 over 1,000 because you remember to convert them. And that should be 0.045 moles per decimeter cubed. That's how you do every single titration question in the universe. There's no other way of doing it. I don't care who you are, who you think you are. This is how you do it. This should have been, everyone should have been getting this. And the fact that 30% did is kind of shocking to me. And I don't think it's an acceptable standard. And we need to aim higher, bro. We got to aim for, we got to get, the bag. We've got to hit 10,000. So the uncertainty in this 25 centimeter cube solution of this is that the total uncertainty of the solution from the burette is that calculate the total percentage error using the pipette and burette. Okay, when you're doing all of this stuff, when you're multiplying and dividing quantities, you have to use the percentage errors, as in you have to add them together. You don't subtract them, you add them. You can't have, if you use a measurement and use another measurement, they're combining their percentage errors is adding them. So percentage error for, let's do it one by one. So the pipette is going to be the uncertainty divided by the thing you measured, 25 times 100. Okay, which is 0.2%. Now for the burette, it's the thing that you measured, so 0.15, the uncertainty divided by what you measured, 24.5 times 100, which is 0.61%. Now, look at these two together. What did you do with these? We messed around with these volumes, didn't we? This is one singular measure we used, this is one singular measurement we used, and we also did them to get these concentrations and this and that, yada, yada, yada. So the total percentage error, is going to be just them two added together. So it's going to be 0.81. Boom, that's how you do it. In the examiner report, it says the answers are generally poor. Many students just added together the uncertainty and the burette of the pipette and the burette together and then just divided by the total volume of both. You can't do that. That doesn't work because this uncertainty only applies to this equipment. This uncertainty applies to this equipment. Saying that this, you can just add those to this and this together and divide it by that, that's not how fractions work. You can't say 3/4 plus, 7/5 is the same as just doing 3 plus 7 over 4 plus 5 because you're implying, which is incorrect by the way, that it's just 10 over 9. If I do 3/4 over 7/5, it ends up being 43 over 20. Are those the same? No, so you can't do that. Don't do that. How have you guys forgotten year 6 maths? So this question is about complexes containing the aluminium ion. Give the electron configuration of Al3+. Well, I know it's in period 1, 2, and 3, so I know it's going to be 3 something at the end of it. I'm just doing Al, sorry. So I know it's going to be 3 something. It's P1. So I know it ordinarily finishes with 3P1, right? So Al normally is going to be 1s2, 2s2, 2p6, 3s2, 3p1. However, they want the Al3+, so we're going to lose that electron, bye-bye. That's 1, and then we lose 2 more, bye-bye. That's it, done. Next. So here, people just kind of added random stuff on the equation for no reason. Look at what the question's saying. So it says here, the anhydrous aluminum sulfate is added to water, and it gives you a solution that contains this complex ion. Write an equation for this reaction. First of all, just write what it's told you. Don't get gassed and try and do it from memory. So here, the question has said that I'm adding Al2SO4 3. What else has it told me? I'm adding water. So I add H2O to this. What am I making? AlH2O6 3+. That's it. That's all I know. There's nothing else it's told me. Now I need to look at this and go, what's happening here? So we've got 2 Als here. It probably makes sense to put 2 there, first of all. So now I've got 2 Als happy days and 2 Als here, right? But I have 6 waters out of nowhere. So I need to sort that bit out, don't I? So 6 waters, but there's 2 of them. So now I've got 12 waters. So I've got 12 H2O there. So these Als are happy. These Als are happy. Those waters are happy. Those waters are happy. What's missing? Well, all these SO4s. These 3 SO4s must, also have a look. No overall charge here. There's a 3+ here. So SO4, remember, is 2-, but I have 3 of them. So you got 3 of them there. So that 2 times 3 is 6, right? And then 3 times 2 is -6. So they balance out. Happy days. So here it says, explain why this solution containing this is acidic. Even if you don't remember the specifics why, if anything is an acid in the universe, it releases an H+, a proton donor, yeah. You'd be surprised how many people can say proton donor and have no clue that it simply means it just puts H+ out. The same for proton, so that's an acid. Any base is a proton acceptor. Yeah, that's great and all, but it basically means that you're gaining an H+. It's shocking how many people can just regurgitate that. So for example, if I have HCl, that becomes H+ and Cl-, right? This is the acid. Why? Because it can release an H+. That's it, right? This is a base because it can gain an H+. It's a acceptor of a proton. There's no point learning buzzwords if you don't know what you're saying. The reason I'm getting spicy about this is because if the question's told you that this is acidic, it means it's putting out H+. You need to think where the H+ are coming from. In here, we've got H2O. That's the only thing with H's in it, right? So HO. In order to shove off an H+, you've got to break that bond, don't you? The OH bond. So for some bizarre reason, Al is very good at doing this, and it's magically able to just break off that OH bond. The reason is because Al3+ has a high charge and it's a small size. It's just what gives it its quirky behaviors. And it has a high charge density. So again, imagine you've got a really high charge here and a small size. If I take that same 3+ and put it in a massive size here, then it's not as dense. It's not as compact, if you will. So it's not as good at attracting and this and that and blah, 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 right? Here, all it's simply saying is that you've got to clarify that the Al3+ is a high charge. 3+ is pretty fat and a small size. Why does that matter? Because what it can do is it weakens the OH bonds in water, leading to the release of H+. That's it. If you release the H+, then it's an acid. So then it's a state where the concentration of aluminium sulfate cannot be determined by colorimetry. What does colorimetry mean? Well, it's using the absorption of light, right? You absorb light, and you look at how much is that. So if you put white light through something, for example, if it's red, okay? If the item is red, then it's going to absorb everything but red. Everything except red, because white light is RGB, it's everything. So what comes out is G and B, and what's reflected is red, and your colorimeter will pick that up. Now it says here that aluminium sulfate for some reason cannot. Well, there's multiple ways you can navigate this. You could just know that it's colorless, but have a think about what makes it a bit different. Well, it's not a transition metal. If it's not a transition metal, it's not going to have a colored ion because the properties of transition metals are except scandium, strontium, and zinc. Now, the reason it can do that is because of that energy gap in those d orbitals. So here's my d orbitals here. Transition metals, when you stick a ligand on them, it splits them there. Ordinarily, it's supposed to be this. Ignoring that, right? But when you add a ligand on, it splits them like that, d orbitals, and this is more energy. So what electrons can do is if you hit them with the right wavelength, the right color of light, the electrons will absorb it and then get moved up to this slightly higher d orbital, and that is your energy gap. And when it absorbs that, everything else is reflected. So for example, if something is green, it's absorbing everything except green and reflecting green back at you. So here, it's not a transition metal, so it's not absorbing visible light, so it's not going to have a color. It's colorless. So if it's not colorless, you can't use colorimetry. There you go. An excess of aqueous ammonia is added to this solution, given ionic equation for the reaction, and then state 1 observation. So a lot of people got the observation right, but they just have no clue what to do with the equation. Just look at what the question's told you. It said here that we're reacting. Yes, it's ionic. Fine. You can write the whole thing and then turn it into ions if you want later. But here, what have we got? We've got AlH2O6 3+. Okay, and then they've told you what else. They're adding aqueous ammonia. Sorry, let me just some more space. They've told you that and that's aqueous, sorry. Then you're adding NH3 aqueous. Fine. If it's ionic equation, the ions have to change. Otherwise, they're just going to be the same on both sides. Well, this is just going to be the same on both sides. So this has to have changed in some way, shape, or form. This has to change of some sort. The question previously has told you that this acts as an acid, and also you should know it acts as an acid. So this can put out protons. It releases H+. If it releases H+, generally it's the number here, that gives it away. These H2Os, you can take one H+ from an H2O. So if this is 3+, I can shove out 3 H+. So if I've taken 3 H+ from that, I now have Al, H2O3, because I've got 3 H2Os left, and then what's left of those H2Os was OH-, and there's 3 of them, which has no overall charge, and is generally, in this topic, if you have no charge, a solid, right? Now remember that from here to here, it's lost H+. Somebody has to gain those. Oh, would you look at that, NH3. What can NH3 form? It can make NH4+. It can act as a base, a proton, etc. It gains a proton. So if we lost 3 H+ here, each one of these only gains 1. To balance that, we need a 3 there and a 3 there. Boom. And then it says observation. I find it so shocking that people have written effervescence and they've just said that. And the exam mark scheme has to include to say don't accept it. How many of you people tried that? Come on, man. Look at what you're making. Aqueous, solid, aqueous. Whoops. You're making a solid. So you're making a precipitate. You need to say what color it is. Remember that it's not a transition metal. It's not able to do all that stuff that transition metals do, as explained in the previous question. So it's a white precipitate. There you go. White meaning it doesn't absorb anything. It reflects it all back. Because remember, visible light has all the mixtures in it, and it's white light. So if it's not absorbing anything, it reflects it back. If it absorbs everything, it's black. It's an object. There's no light reflected back. So an excess of dilute sulfuric acid is added to the products of the reaction in this. Identify the aluminium species produced. So they're adding an excess of this sulfuric acid to this. What's going to happen? Every single acid dissociation reaction is reversible, as in this is, remember, acting as an acid because it's losing them H+, so you can actually go back. Here, it's saying you're adding an excess of sulfuric acid to the products of this reaction, to this and this. Now, sulfuric acid, remember, puts out H pluses. So it's not really going to do anything with this because this has too many H pluses. This is technically an acid because it can lose them to go back there. So it's not going to do anything with this. It's going to do something with this. All acids react by giving H pluses. This one is short of H pluses now, isn't it? So it's technically a base. So this can gain H pluses back. How many can it get? Well, these can all become H2Os again. So what you end up making is you go backwards. You go Al, H2O, 6, 3 plus. That's it. It's not some magic hack or anything. I'm not a magician and I just don't memorize. I've never seen this specific style of question, or maybe I have in the previous tutorials, but I don't remember it. It's not like I'm some genius and I'm like, oh my God, I just know everything. I know every single question in the universe. It's like, you've got to just look at what's happening. And I like the way I think of it is that this is this type of substance, this is that. And then this is an acid. Any acid is going to react by giving H pluses. The rest is whatever. The H plus is the important part, right? So something about this H plus is reacting with this. Well, here to here, I lost H pluses, so I'm just putting them back. That's kind of the thought process I'm using. So figure 3 shows the structure of an EDTA4- ion. Atoms of two different elements can form coordinate bonds with an aluminium ion. On figure 3, draw circles around the atoms of the two different elements that would link to an aluminium ion by a coordinate bond. In order to make a coordinate bond, what do you need? Anyone? You need lone pairs. You need to know where the lone pairs are. There's some here, there's some here, there's some here, there's some here. So that's this one, this one, and this one, and this one. So there's at least that. Not these, they can't. Now, we need to look at where the other lone pairs are. And what other thing can have lone pairs? Nitrogens, you should always have a quick look. Nitrogens in group 5, so 1, 2, 3, 4, 5, right? If it's got 3 H's or 3 carbons or whatever, like in this case, these are all single bonds, as in there's a single electron from that carbon, right? So here's a carbon's electron, here's a carbon's electron, here's a carbon's electron, right? So those are all bonding pairs, bonding pairs, bonding pairs, lone pair, right? So this has got 3 bonds on it. It's still got lone pair. So there's one and there's one. So those are the answers. There you go. Right. Now, again, if you've seen my previous video, you'll know I'm an absolute hater on this. So we're at the dreaded back titration question or whatever, right? Like, I hate when people complain about this because, again, like, it's just, they don't read. They just kind of either do random stuff or they just do what they think works. Like, read the question and make sense of what's going on. First of all, okay, basically, they've told us that this hydrated aluminium sulfate AlSO4 3X H2O is soluble in water. Great. They said you could find what X is and the relative formula mass by titration. Great. And then there's all this information. You are not reading all of that and you're not taking it all in. I'm not. I can sit and read all of this, but I literally won't process any of it. Like, I'm just going to forget. So what people do is they'll just jump and try and take shortcuts and they'll work out, oh, I see this and this. Okay, I'll just do this times this. And now I've got moles. And then I'll try and do whatever random crap I can by jumping back and forth. Like, why are you doing that? What I always suggest you should do, and watch my video on it as well, the back titrations video, is you always go through line by line, pick out a number and decide who it belongs to. Okay? So what I mean by that is method, dissolve. Okay, here's a number, here's a mass or a quantity, like a volume or anything, right? So I've got a mass of 1.036 grams. Who does that belong to? Well, it belongs to this, right? So Al2SO4 3.XH2O. Great, carry on. Okay, I see a volume here. Who does this volume belong to? Well, if I read the whole sentence, we dissolve this much of this in distilled water and made up to 250 centimeters cubed. So this 250 centimeters cubed contains this. The water doesn't matter. Like, who cares? It's just water. We're just adding that to dilute it, right? This whole 250 contains this much of that. So that volume is now 250 centimeters cubed. So then the next thing you should think is, if I'm adding anything to this, you add a nice big plus. If not, you're moving to a next step, right? Or like you're doing something else. So my next step, maybe, or I don't know yet, it says add 25 centimeters cubed. So I see a volume. Are we adding anything to this? No, we're not. So 25 centimeters cubed, I write V equals 25 centimeters cubed. And then I decide who does it belong to. So a lot of times I ask people this and they say, this solution. Does this solution say anything useful? No. Add 25 centimeters cubed of this solution. That's not sufficient. You need to say who is in that. Who is it? 25 centimeters cubed of this solution was from this first part. What's in it that's actually reacting or that we care about? Well, it's this. The Al2SO4 3.XH2O is in that 25 centimeter cube. It says add, this is a 2, so we're adding something to this, right? And we can see there's a volume of 50. Who does that volume belong to? The solution containing EDTA4-. EDTA4-. Great. And I can see concentration. Who's that concentrations? It's EDTAs. So you're going to write that there. C equals 0.100. Right? And then it says determine the excess of EDTA4- by titrating with ZnSO4 solution. Okay, so you now need to think the next step is they've got excess EDTA4-. You know that's what you're messing with. Great. So the excess of EDTA4- ions requires, here's a volume of that. So whose volume is this? You write the volume somewhere. Volume equals 18. Who does it belong to? The excess of this requires this much of this much, this thing. So it's ZnSO4's volume, not EDTA, which is a common mistake because people can't read. ZnSO4, right? I can see a concentration. Whose concentration is that? It's this, 0.0105, right? And it reacts completely. So now we know that this and this react, but you've got an excess as well, right? And then that excess reacts with this. Cool. The next bit you should do is once you've now made your little flowchart of events, you then add molar ratios to this. And then, and only then, can you start working out moles and doing all the other crap. If you try working out moles preemptively here, you're just going to go wrong. I can guarantee it. I've never met a single person in my 7 years of teaching who's done it successfully by just looking at the question, reading it, and going moles. You need to do this. So the equations for this reaction is this AlH2O6 plus EDTA 4 minus gives you this and this, right? So this AlSO43, if you dissolve it, it's going to make that complex. So we know it's in a 1-to-1 ratio. Okay, so 1, 2, 1. Now, this is the EDTA4 minus reacted with the Zn, and EDTA4 minus. It is in a 1, 2, 1. And actually, while we're here, the excess EDTA will also just be whatever's left over as well. Fine. Okay, so then it says, and then they've also given us the MR as well, conveniently for that. So I'm going to just scribble that somewhere as well. Al2SO43, and its MR is 342.3. So now it says, use this information to find the MR of this whole thing and then find out what X is. So I actually straight up don't need anything else from that text anymore because I've now got everything I need. I need to find the MR of this. The only starting point I have is this volume and concentration, which people will validly work out and then completely fumble everything else. So let's start with the basics. This is the moles of the ZnSO4. So the moles of ZnSO4 is going to be its volume, so 18 over 1,000 times 0.0105, which is 1.89 times 10 to the minus 4 moles, right? Now, who did this react with? Look at your flowchart. Was it this? Was it this? Was it this? It reacted with the excess EDTA4 minus. Therefore, on that basis, we know that the moles of the excess, and make sure you write it like this so you know what you're doing. And if you get it wrong, the examiner can at least know what you're doing and you can get method marks. The moles of the excess EDTA, well, if they're in a 1-to-1 ratio, that must also equal 1.89 times 10 to the minus 4 moles. Excelente. So now you know that the moles of that is that. Great, now what? Well, they've given you this volume and concentration of the total amount of EDTA, right? So that means out of all of this, some of it would have reacted with this and some of it's the excess. So if I work out the moles of the total EDTA 4 minus, which is going to be its volume, 50 over 1,000 times 0.0100, it will be 5 times 10 to the minus 4. So now we can work out the moles of the EDTA4 minus that reacted by just doing their difference, right? So it's just going to be 5 times 10 to the minus 4 minus 1.89 times 10 to the minus 4, which is going to be 3.11 times 10 to the minus 4 moles. Now, this reacted with all the AlH2O6, not the Al2 stuff, blah, 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 because the equations told you these two react, not this whole thing. So stick with that. So the moles of the AlH2O6 3+, however, there's two of them. It could be either from here and here. Be crystal clear where that is in 25 centimeters cubed. Is going to be the same as the EDTA reacted. So it's going to be the 3.11 times 10 to the minus 4 moles. The reason you should do that is because it forces you to remember that the question wants you to do this one, not that one, right? So if this is 25 centimeters cubed, we need to get to 250. So the moles of this Al blah, blah, blah into 50 centimeters cubed is going to be the end divided by the first, so 250 over 25 times the 3.11 times 10 to the minus 4, which gives you, if I just put it down here, 3.11 times 10 to the minus 3 moles. Okay? Now, this is the moles of AlH2O6 3+ into 50, as in all of the AlH2O6 3+ here. However, the question wants us to work out this. Now, if you have Al2SO4, like 3, if you dissolve that, because this is a solid, remember, if you dissolve it, that's going to make 2 Al3+ and SO4 2-, but 3 lots of them, okay? Those two, every single Al3+, is going to, join with one on the waters and this and that, blah, 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 and eventually become AlH2O6 3+. So if we have the moles of essentially what is this, right, we want the moles of this to be able to mess around with those numbers. So can you see how there's a 2-to-1 ratio of this as well? So the moles of the Al2 blah, 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 blah is actually going to be 3.11 times 10 to the minus 3 divided by 2, which is going to be 1.555 times 10 to the minus 3 moles. Now you have the moles of the Al2 blah, blah, blah. We have its mass, which was 1.036. Its MR is just going to be 1.036 divided by the 1.55 blah, 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 right? That we just worked out here. If we do that, that gives us a value of 666.2. And remember, that's this Al blah, 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 blah with the dot XH2O. So this dot XH2O has to be the 666.2 that we just worked out minus the MR of it without the H2O, which they've told you, where's it gone? It's somewhere here. There, this. And I've also written it there. So 342.3. So the difference of those are going to tell you the XH2O. So minus 342.3, right? So then on that basis, XH2O is going to equal 323.9. So then you can find out what X is by just doing 323.9. Sorry, I don't know why I'm saying dot. Whoops, divided by 18, which is 17.99, give it up, it's 18. There you go, that's how you do every single one of these ever. Okay, so this question is about fuel cells. In a methanol-oxygen fuel cell, this overall reaction is as follows. At the positive electrode, oxygen reacts with hydrogen ions to form water. Give a half equation for this. Again, unfortunately, there is an element of memory to this, but you can just look at like the equation and what they've told you. So they've told you that oxygen reacts with hydrogen ions to form water. So just put that in, right? O2, we're reacting with H plus, makes water. Cool. Now the rest you have to unfortunately work out. However, there's some clues you can use. You know it's a positive electrode. Remember that if we're doing, it's either oxidation or reduction. So if you're, imagine that's like an electrode, right? If I'm oxidizing, I'm putting electrons into it. So electrons moving into this, or like away from it to whatever. So that's going to be negative. Whereas if I'm reducing, I'm yanking electrons out, aren't I? So that's going to be positive. A way to remember it, anox, red cat. Anode, oxidation, reduction, cathode. So on that basis, whatever I'm messing about with here, the electrons have to be on this side because it's being reduced. Something is, right? So it's E minus. Let's have a look at who's being reduced. So a lot of people are very, very reluctant to use oxidation numbers. Like they're your best friend. Because if you've got equations where you don't know what's really happening, look at the oxidation numbers. It helps because if something's getting oxidized, something else has to be reduced. However, this is a half equation, so you are allowed to have either oxidation or reduction. That's why they're called half equations, because you can't really oxidize without reducing something else. So if you have one of them, you've got half the equation. So anyway, H is +1, it stays as +1. O is going from 0 to -2. Oh, would you look at that? So you can't have like fractions of an electron. You have to, balance it out like fully, if you will. So while it'd be tempted to be like, oh, let's just put a half here and I'm so clever, right? You can't half electrons. So let's balance all the elements out first. So we've got 2 oxygens here, 2 oxygens there. So then there's 4 H's, 4 H's. Cool. Each one of those is going from 0 to -2, but there's 2. So that means you're going to need 2 electrons to get there. But there's 2 of them. Remember O2? 2 O's there. So it's not 2 electrons, it's 4 electrons. Boom. That's how you do it. Now, at the negative electrode, methanol reacts with water to produce CO2 and hydrogen ions. Give a half equation for this. Again, just follow what the question's telling you. So it's a negative electrode, so it's going to be oxidation. Something's getting oxidized. It's methanol, CH3OH. It's told you it's reacted with water, H2O, and then you're making CO2 and hydrogen ions plus H+. So if it's oxidation, we know electrons are going to be on this side. Great. Now let's balance everything else out first, and then we can mess about, right? So C, happy days, great. O, and O, actually, happy days. Okay, CH3OH, well, there's 1, 2, 3, 4, 5, 6. So put a 6 there. Now we need to decide who's actually being reduced. Okay, so if we look at the oxygen, -2, +1, that's all happy, nothing there, because it stays as +1 there, doesn't it? Okay, that's a +1, that's a +1, that's a -2, right? So there's 3 lots of that, so it's going to be +3. So +3, +1, -2, that's 4, -2 plus, why can't I do maths? That's going to be +2, so the carbon here is got to be -2. Now let's look at the other carbon here. So that's going to be -2, but there's 4 of them, so -4 plus 4. Whoa, would you look at that? You're going from +2 to -4. So what's happened? Obviously, the number's gone up. It's becoming oxidized. How many electrons have you lost? You must have lost 6 electrons. Boom, there's where 6 electrons comes from. That's how you do these every time. Okay, so the standard electric potential for this is that, whatever, calculate the standard electric potential for this electrode. So an E cell is E reduced minus E ox. Okay, what you do is look at what you have information-wise. So they've told you the standard electric potential for this electrode is that. Now, from the previous part of the question, it's told you that this is the negative electrode, and we've established that it's oxidized. So this is the one that's being oxidized, right? Let's look at the other numbers in the question. They've told you that this fuel cell, the overall equation is that. So which one is that? Which value in this formula is that? Well, that's the E cell, isn't it? The whole one. So then now you know that E cell, or the total E cell is going to be what? Sorry, 1.20 equals whatever's reduced, which we actually don't know, minus whatever has been oxidized, 0.03. So in order to find E reduced, which must be this one, and also the question kind of, we can work it out from there as well, cough, right? But, oh my God, move on, right? The E reduced has to just be, well, if you rearrange it, E reduced equals 1.20 plus 0.03, which is 1.27. So reading your question is your best friend. Now it says statewide fuel cell does not need to be electrically recharged. When you electrically recharge something, you're forcing it to go the other way, okay? As in you are like switching the reactions around. Now, here, this reaction, these fuel cells will have, all fuel cells will work as long as you provide them with fuel. So if you continually give them fuel, they work. So that's it. You don't need to do it because as long as you give them methanol and whatever it was again, oxygen, it will do its thing. So reactants are constantly supplied. Otherwise, why are they called a fuel cell? What's the point? State one advantage of using methanol rather than hydrogen in a fuel cell in cars. It's the base. So here, a lot of people tried saying stuff about flammable hydrogen. What methanol is an alcohol. That's flammable too, so that's already gone. Generally speaking, saying safety, cost, and greenhouse emissions is a load of crap as well. You need to think carefully about what fundamentally is different. Well, methanol is a liquid and hydrogen is a gas. And also, the reason I magically know that is because look at the question has told me that. So, which one would you rather carry around? A liquid or a gas? If you want a gas, you have to compress it with high pressures, and if something dents that thing, boom. Even if there's no fire. Whereas methanol's a liquid. You don't have to mess around with it. You can transport loads of it. So methanol is liquid, easy to transfer. That's it. Or transport. Sorry, whoops, I should say. Transport. There you go. So this is a question about time of flight mass spectrometry. Give the equation, including state symbols for the formation of that and that. So, okay, thank God the majority of people got it right, but just use again what the question's saying. You're making SR plus ions, right? And obviously we kind of have to use a bit of our brain here. We have to put state symbols in as well, because it says, including state symbols. We're making it 1 plus ions from atoms. That's the first ionization energy, where 1 mole of gaseous atoms, right, become 1 mole of gaseous 1 plus ions. However, we're using electron impact, so we kind of have to switch it up a little bit. But start with what the question's told you. It's a gas here, and we've got SR, and that exists as a gas as well. Sorry, whoops, because remember, we're using gas. Now, here, we're using electron impact, which means you're slamming it, you're adding electrons in, so you have to put E minus there. You can't get away with it, right? However, electron impact works by knocking electrons off of this. So now what you have is an electron's been knocked off of this, so you're going to have an E minus, but then you've also got this one left over from before, so it's this. There you go. It does allow just that to this, says in 1 electron, but like, come on, man. Fine, whatever. Now here, every single year, pretty much, there's a question that's exactly like this, and we still keep seeing people getting it wrong. 36% of people got all marks. What was happening here, man? What are we doing? Don't follow routines. It just doesn't work. Read the question, use your brain and reading comprehension skills. A sample of strontium is analyzed by time of flight mass spectrometry. The sample is ionized with electron impact. The ions are accelerated to have a kinetic energy. So again, use the little thing before I was saying about like just writing the numbers down so you know who's who. 7.02 times 10 to the minus 20. Great. An ion takes, so time is going to be 9.47 times 10 to the minus 4. And they've told you the length of the flight tube is 95 centimeters, right? They've given you this formula, kinetic energy, where the mass has to be in kilograms, the velocity has to be in meters per second squared, right? That's in seconds, that's in joules, and this is the kinetic energy as well, which is in joules, and that's in centimeters. In order to mess around with this formula, because it's told you that it's in meters per second squared, you have to change that to meters. So that's going to be 0.95 meters. Anyways, so it says here, use this information to deduce the mass number of this ion. Every single mass number you see in a periodic table, what unit does it have? A lot of people can't answer this question. The mass number is measured in grams per mole, as in grams per 1 mole. Whenever you see like something per something, it means, that for every one of them. So for example, if it's like, I don't know, moles per decimeter cubed, and if I have 5 of them, it means that there's 5 moles for 1 decimeter cubed. So here, it's really important you remember and appreciate that the mass numbers on your periodic table are this unit, because that's where everybody fumbles, and it comes up over and over and again, and people still fumble it. Anyway, so we need this information to figure out the mass number of this ion. So we need the mass from the kinetic energy, right? So start by rearranging the formula, because that makes most sense. So 2ke equals, so if I times everything by 2, it'd be 2ke equals mv squared, right? So if I just want m is going to equal 2ke, right? That gives us a fraction divided by v squared, right? We don't have the v. So we have kinetic energy, that's great, but we don't have v. So let's just use our brains for a sec. Velocity, how do we work that out? It's going to be distance, or displacement, going to be cancelled, whatever, distance over time, right? And it's in meters per second squared. So we now know that, well, they've told you the distance it's traveling is 0.95, and the time it's doing it in is 9.47 times 10 to the minus 5. 10 to the minus 4, sorry. So its velocity is going to equal whatever that is, which is 1003 meters per second. Great. So now you put that into the formula. Mass equals 2 times 7.02 times 10 to the minus 20, all divided by 1003, which is going to equal 1.396 times 10 to the minus 25 kilograms. But what are we actually working out the mass of? Everyone loves doing this, and they don't know what they're doing. This is the mass of a single ion, of 1 ion. The question wants the mass number of the ion, which is grams per mole. So anyway, whatever, we've got kilograms, we need to make this grams, so it's going to be 1.396 and then times it by 1,000, so times 10 to minus 22 grams, right? But that's the mass of 1 ion. So they want the grams per 1 mole, right? We only have grams per 1 ion. So if we have only 1 ion, how many is in a mole? If I have 1 mole of bananas, I have 6.022 times 10 to the 23 bananas, okay? 1 mole is just a measurement. It's just saying this. And here you can see that there are 6.022 times 10 to the 23 of some things for every 1 mole per mole. That's what the unit tells you. So if we have, this is for 1 ion of them. If I want 1 mole of it, I'm going to need something's grams per every 6.022 times 10 to the 23 ions. If I know that this 1.396 is for 1, how do I get from here to here? I times it by 6.022 times 10 to the 23. So it's going to be 1.396 times 10 to the minus 22 times 6.022 times 10 to the minus 20, sorry, not minus 23, to 23, which gives you a solid 84.04, which is 84. That's how you do it. This should be 3 marks, man. Come on, no excuses. So explain how the ions are detected in the time of flight mass spectrometer, and then state how the relative abundance of the ions is determined. A lot of people say a current's made, but then that's it. And then a lot of people just didn't really address how we got this. So the whole reason that we get a current is because the whole point is you're slamming this thing. Every single thing you do in mass spectrometry, the first step is always making a positive ion, right? Now, the whether you do electrospray ionization or electron impact, you're going to make a positive ion. Current, by definition, is the flow of electrons, like the movement of electrons, okay, per unit time. So you can't really have a current if the electrons aren't moving, okay? So if you have a current, you have electrons moving, you need to figure out where the electrons are moving. Well, you're shoving positive ions towards it, positive ions, electrons are negative, those ions are gaining them electrons. That's where it comes from. So how do the ions are detected? The ions hit the detector and gain electrons, and the movement of electrons causes a current. Because a current, by definition, is you have to have electrons moving, or like a moving charge of some sort. Now, how do you get the relative abundance? The abundance is how much of the movement of the electrons you have is, as in the current. So the current is proportional to the abundance. Because if you have loads of ions, you're going to have loads of electrons moving. If you have no ions, you're not going to have any moving. So as the number of ions smacking that detector goes up, the number of electrons moving, because they're taking them, goes up. So it's proportional, and that's how we can calculate things like that. So now it says a sample of strontium contains these 3 isotopes. 82% of it is that. The other isotopes are in a 1-to-2 ratio. Calculate the percentage abundance of 87 in this, and then use it to work out the relative. Okay, right, great. So now, a sample of strontium has these 3 isotopes. 82% of it is 88 SR. So 100% is obviously the total of anything. We've been told that 82% is the 88 SR. So the remaining 18 has got to be the 86 SR and the 87 SR. They've told you that the remaining of this split, if you will, is split in a 1-to-2 ratio. So this 18 is split into 1-to-2. So how do we work out splits and ratios again? What you do is you add up the ratio. So 1 plus 2 is 3. And then you work out what 1 share is of the ratio, as in one of them. So it'd be 18 divided by 3. So 1 share is 6. So if it's in a 1-to-2 ratio, what you really have is you've got 6 to 12, okay? So it's a 1-to-2 ratio of 86 to 87. So it's going to be 86, and 87. So now you know what percentages of either of them are. So then to work out the relative atomic mass, you would just do the AR is going to equal the mass of each one times their percentage abundance. So 88 times 82 plus 86 times 6 plus 87 times 12, and then divide by the total of all their abundances, which is 100%. It doesn't always have to be 100, it's just the total of whatever it is. If you do that, you get 87.8. Done. Electrospray ionization is sometimes used instead of electron impact for the ionization of a protein in mass spectrometry. Suggest why. Okay, so this is a very niche fact, a kind of side fact that AQA doesn't really focus on very much. So when you're doing mass spectrometry and you're doing that first step where you're either doing electron impact or electrospray ionization, what can sometimes happen is you can get lots of different peaks in your spectrum, and the reason being is because you're fragmenting it, you're breaking it off. So for example, if I have this skeletal formula here, it literally just breaks it into tiny chunks like that, and then the rest. So that's called fragmentation. So here, the question is saying electrospray ionization instead. If they're choosing one over the other, the only thing I can think of that would explain it is that you've probably just got some fragmentation. That's it. So here, the protein doesn't break up or fragment. That's it. There's nothing else really you can use as a cue in here. A lot of people just said denaturing. Denaturing is where you change the tertiary structure of it because of the changes in hydrogen, ionic disulfide bonds, and all that jazz. We're not really doing that here. We're just physically breaking it. That's the problem, because all we're doing is working out the mass of the whole thing. And in order to do that, all you need is a 1+ ion. Boom. So that's all I can, say for that. Okay, so this question is about weak acids. Here's the pH ranges of some indicators. Identify the one that's best suitable for propanoic acid and sodium hydroxide. So for some reason, people said bromothymol blue is the most common one incorrectly. What's going on? You can't just look at it and be like, yeah, I know this, I'm the goat. Where's the thought process? Quickly think of a pH curve in your head. Just do a quick sketch of a pH curve. So 0 and then 14 or whatever, right? So if I'm doing a weak acid and then there's 7, the pH is probably going to be 4 or 5. It's going to be a bit crap. And then the strong base is that. So start there. I add my strong, and I'm starting with a weak acid. I'm adding the strong base. So then what happens? It goes up and then like this, right? So your equivalence point kind of lies with like the vertical bits here. Now, when you choose an indicator, you want to make sure that, remember this, as you go this way, you're adding more of whatever. So here we're adding more base. You want to make sure that when you add base, you want the most drastic change in color possible, right? So yes, you want it where the vertical bit is, but you want it to be as tiny of a range as possible, because that way you don't, like, you know exactly how much you're adding. Because imagine, for example, if it was like a really, really like crap range like this from here to here, you don't know if you're adding, like, and the color change only happens from here to here. You know, you have to add like either that much or this much, like this massive difference, right? And then and only then you get a color change. So you can't really get an accurate result. Whereas if it's a tiny, super sharp change here, right, you can either do this or this. So you've got very little wiggle room for like making mistakes. So you want to choose something that sits within the range that would make sense of where the vertical is, but you also want something with as sharp of a change as you possibly can as well, like as in the narrowest range as well. So on that basis, bromocresol green is absolutely not, like, that's not going to work. Like, it's nowhere near like where that's going to be. So it's out. It's going to be shifted more towards above 7, wherever this one is. Bromothymol blue is a bit too low. Like, like this range is from 6 to 7, but like if we're starting with the weak acid, finishing with a strong base, it's going to go way above 7 before, you hit that equivalence point. Well, not way above, but above it. So that one's out. Thymol blue is the one. And also the range is pretty tiny as well. There. Give an expression for the acid dissociation constant for Ka propanoic acid. It's surprising. A lot of people forget that's just a Kc. That's all it is. So when they get a question, be like, why does the temperature change the pH? They're like, I don't know. Like, it's just like every other one. So the dissociation of this is going to be CH3CH2COOH, right? It's going to dissociate into CH3CH2COO minus because it's an acid and it means it puts out an H plus, and then it's going to have the H plus on the other side as well. So it's products, concentration of products over the concentration of reactants. It's going to be H plus, equals H plus CH3CH2COO minus. Make sure those are square brackets all over the acid, which is CH3CH2COO. Done. Now it says calculate the pH of a 0.1 mole per decimeter cube propanoic acid solution and then give your answer to 2 decimal places. Now here, what happened? 63% of people got the answers. I think it should be full 100%. The way to do acids and bases and weak acids and bases is HA is the acid. Generally, this is for weak stuff. A minus is your salt, not the base, because OH minus is your base that you're going to do. If we're talking acid plus a base makes a salt plus water. That's the overall fundamental reaction ever. HA plus a base, which is OH minus, will make a salt, which dissociates to A minus and then water. Now, the reason I'm saying that is because these letters, if you follow them consistently, you'll do everything just fine. If you're trying to find the pH of anything, you need the H plus, right? So if I have a weak acid, we need to think of a formula that has H pluses in it and links it together, right? So your options are Ka equals H plus A minus all over HA, and then Ka roughly equals H plus all squared over HA. There's specific scenarios where you're supposed to use one over the other. I've had people sometimes say, oh, it's because you have more H pluses in this. No, it's completely wrong. There's different scenarios when you use them, and look at what's in the equations to tell you what it is, right? If I look at this, H plus is going to be in every single one of them because I'm looking for H plus. So that don't matter. A minus, what does A minus mean again in weak acid? It's the salt. So here you have salt, and then what's HA? You've got an acid. So you use this one when you have a mixture of I should say weak acid really, a salt and weak acid. What's that called when you have a salt and a weak acid mixed together? It is a buffer. Right here, what do we have? We have no salt, we have weak acid only. So on that basis, you use this when you have a weak acid only. That's it. And then if you want to find, if they say find the pH of a base, what people do for some reason is they're like, oh, I need to do something with the pOH, and it's like, what are you doing? Every single pH measures H plus. So you need to find H plus's concentration. You have a base which is OH minuses, so you need a formula with H plus and OH minus in. Which one is it? KW. KW equals H plus OH minus. That's it. Because if you're ever finding a pH, you need H plus. If it's pOH, then you would use this, but it's not, right? That's how you do every single one of these ever. And it's really important you stick to this like your life depends on it. A minus in a weak acid is salt. HA is a weak acid. The reason we say it's H plus squared is because the dissociation is so far to the left. For example, HA becomes H plus A minus, right? Because there's such tiny dissociation, you can have like 0.00003 and like 0.00004. Like they're practically the same. They're so tiny. That's why we do this. Whereas if you mix a salt in, you just added a hell of a lot of A minus in. It's now messed everything up. So now you have to consider it. So back to the question for my side ramble there, because it's one of my favorite topics. It says find the pH of this propanoic acid solution. Think, do we have a weak acid or do we have a weak acid and it's salt? We have a weak acid only. So we're going to use Ka equals H plus all squared over HA. Right? Now, what information do we have? Well, sorry, let's rearrange this first. So then H plus is going to equal Ka times HA, right? And that's H plus squared. So all I have to do is square root that. Now, let's see what information we have. Do we have the concentration of HA? Yes, we do. Do I have Ka? I have pKa. P of anything is just negative log 10 to whatever that is, okay? So if I want to undo, like how you undo the pH to do 10 to the minus, to get to get Ka again, I just do 10 to the minus 4.87. The P just means I'm just doing like my negative log 10. So that means H plus is going to equal the square root of 10 to the minus 4.87 times 0.1, which gives you 1.16 times 10 to the minus 3. And then pH is negative log to the base 10 of the 1.16 blah, blah, blah that you got. And that gives you 2.94. There you go. It should be 3 marks. 10.4 then. So 29 people got all marks. It should be 100. Because if you, like, the reason people do this is because they don't read the question, they don't do blah, 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 whatever. The only way you should ever do this, in my opinion, is by using your brain and by reading the question and following it logically. The questions told you that they're mixing sodium hydroxide, a strong base, and a weak acid. So every single equation for acids and bases follows this. An acid plus a base makes a salt plus water. Now, I say this is the only way you should ever do this, in my opinion. And also you should write the letters to make your life easier. Acid, we call that HA. If we're reacting it with a base that's not its conjugate base, like as in we're just reacting it with an alkali, it's going to be OH minus. The salt is A minus, and the water is whatever, who cares? You're going to react these two, so that's going to go down, that's going to go down, that's going to go out, that's going to go up. So you can't really do anything unless we know by how much. So what you do is you work out the moles before reaction. A lot of people say initial. I think that's a load of rubbish. Make it clear to yourself it's before it's reacting. Because what people mistakenly do is they'd be like, okay, if it's initial, if a question said, after the reaction, there was this many moles, then they'll say that mistakenly there. So make it crystal clear to yourself. Next is your change, and this is the mole after the reaction. And because all of our equations need concentrations, we need the concentrations. So how you do this is you don't look at the question, try and be clever and go, oh, back and forth, back and forth, back and forth, being like, oh, I put this here, this, that. You don't do that. You go and follow this every single row one at a time, because then you don't miss anything and then you don't put numbers in the wrong places, because I've seen so many people do this. So what I say is, okay, I want the moles of the acid. Let's see if the question tells me it. Can I find it? So acid is butanoic acid, blah, 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 is added to 25 centimeters cubed of this. So the moles of this will be 25 over 1,000 times 0.1, which is going to be 2.5 times 10 to the minus 3. So I've done this one. Let's move on to the next. What you do not do is look at the question and try and work back and forth. You force yourself to say, I want the moles before that reaction's happened. Is it there? Yes or no? Okay? Because it means you'll see why anyway in a sec, why. So base then. Do we have a base in? Yes, we do. We have sodium hydroxide. Not sodium, like for example, sodium ethanoate wouldn't count, that's a salt. So sodium hydroxide does. What's its volume and concentration? Well, it's here. So you can do 20 over 1,000 times 0.1, which gives you 2 times 10 to the minus 3 moles. So then what people do is they go straight down here and do everything else. No, you've got to work through everything. None of the formulas have H2O in it, so we don't really care. Do we have any salt before the reaction happens? Pause and let's have a think. What do you think? So, before the reaction, do we have any salt? Well, they haven't reacted, and they haven't told you that they've had any, so it is 0. Cool. How's it going to change? These two are going to react with each other. They're both going to go down. What people love doing is be like, oh, we've got a limited reactant here. Like, who cares, bro? Just like, you can just try and aim to make one of them 0, and then you'll probably figure it out. All right, 2 times 10 to minus 3, 2.5 times 10 to minus 3. There's clearly less of that. So after these two all react, it's going to be 0. If that went from here to here, then that's going to be just minus 2 times 10 to the minus 3, right? Because these are 1-to-1, butanoic acid and this, and it helps to write 1 mel acid, 1 base as well for the future. Sorry, I should have done. One of these going down will also mean one of these will go down. So if I went 2 times 10 to the minus 3 down, this will also go down by 2 times 10 to the minus 3. So minus 2 times 10 to the minus 3. That leaves you with 0.5 times 10 to the minus 3. If these two went down, those must have gone up. So if this went down by minus 2 times 10 to the minus 3, and that did, this will have gone up by 2 times 10 to the minus 3, because we're in a 1-to-1 ratio. So that means we now have 2 times 10 to the minus 3 of the salt. Now we need the concentration after this reaction. Otherwise it don't work. So what people then do is they get gassed and be like, okay, well, this is this over that, and then this is that. Like, think for a second, you just mix these all together. So the new concentrations are going to be 0.5 times 10 to the minus 3 divided by the new volume, which is these two added up. So it's going to be 45 divided by 1,000. There's nothing here, so we don't care. And there's going to be 2 times 10 to the minus 3 over 45 divided by 1,000. If we do that, we now end up with 0.0111 moles of this, 0 of that, and then 0.0444 moles of this. And then what people do is they completely forgot what they just spent all that time working out and then go and do something completely random and get it wrong. Look at what you just worked out. We just found the concentration of HA and the concentration of A minus, So that means the formula we're going to use is Ka equals H plus A minus all over HA. So let's rearrange that. So Ka times HA all over A minus is going to equal your H plus. H plus is going to therefore equal whatever the Ka was. Did they tell us? It is, 1.51 times 10 to the minus 5, 1.51 times 10 to the minus 5 divided by the A minus that we just worked out of 0.0444, right? Times the HA as well, which is times 0.0111. If you do that, you then get a H plus of whatever it is, and then you just pH negative log the base 10 of that, and then you get your answer, which is 5.42. There you go. So now it says a student plans to titrate butanoic acid. So what type of thing is that? That's a weak acid. So it's going to write weak acid here. And that's a solution of ethylamine. So what's that? Well, remember, acids will react with bases. So in that case, it's got to be a weak base. So if we want to, it says here, why can't you use an indicator? Well, if you have a weak acid and a weak base, its pH curve is just going to look like that. And if you choose, for example, an indicator that changes from here to here, even if it's narrow, can you see how, like, let's say this is like, I don't know, this is color X and that's color Y. Whoops. To get from color X to color Y, I have to add all of that. The change is way too gradual. It's not sudden enough. Whereas if it's a strong acid, strong base thing, even if it has the same range, can you see it's there to there? The difference from X to Y is so unbelievably tiny. Like you add the smallest amount of substance and then it suddenly changes. So it's not because the pH range is small. You wanted to have a small pH range. It's also nothing to do with the equivalence point being too short. It's that the change is not sharp. Because if you have methyl orange, that goes from, yellow to orange to red. You want it to go from a very obvious yellow to a very obvious red. Not like a shade of kind of like a nice amber. Like what kind of use? That's not useful, bro. So here, because it's a weak acid, I'm going to be lazy and just say weak acid and weak base. Obviously, you write the whole thing. The pH change is too gradual. Whoops, change is too gradual. So it's hard to gauge when the endpoint is. The endpoint is the moment you add one tiny drop, it's done. The reaction changes, the color changes, it's done. Can't do that if it's too slow. So there you go. That's how you do it. I hope that helps. And please share this video with your friends and this and that, and good luck.